This is a test of my home recording studio for Biology 322, and I'd like to, let me use a darker pen here. I would like to explain equilibria with rate constants. We're not doing a lot of kinetics in this class. It's covered quite thoroughly in undergraduate. A lot of things are covered in the undergraduate course that you should have reference to, but I want to explain some of these ideas that we see more commonly in papers and how the experimental methods relate. So let's consider for a simple reaction, A in equilibrium with B. This could be a chemical reaction, this could be a conformational change, this could be native and unfolded proteins, could be conformational change, and a protein would be a very typical for what we've seen. So we will describe it like this, in which the formation of B relies upon the concentration of A and the forward rate constant, and the formation of A depends upon the concentration of B and the reverse rate constant. So we see that the change in concentration of A with time is going to be equal to the reverse rate constant times the concentration of B, subtracting the disappearance of A, which is going to be the formation of A and the disappearance of A times so this is the concentration of A times the forward rate constant. Okay, and at equilibrium, the concentration of A and B is 0, right? This is the definition of equilibrium. Equilibrium is that the concentration zone change. No more changes occurring. Okay, so we can rearrange that, and we can say then at equilibrium that Kr times the concentration of B is equal to Kf times the concentration of A, right? At equilibrium, these are equal, therefore we move on to the other side of this. And if we recall the definition of the equilibrium constant, which is something that we can measure at equilibrium by the actual concentrations. So if we have something at equilibrium, we can measure these concentrations, and we know that's the equilibrium constant. We can relate that to the free energy change, but we know nothing about the rates. We know nothing about the on rate and the off rate. So here we can relate that, because this then change, it gives us, substituting this into that equation, we end up with the equilibrium constant being equal to the forward rate constant divided by the reverse rate constant. So that means that if we can measure this equilibrium constant by concentrations of these, and we can measure the off rate, so I will call this on rate, off rate, we then know the on rate. So we can we can leverage that along with the Gibbs free energy equation to extract more information. So this is a very commonly done. We may know this equilibrium constant, and if we can measure the off rate or the on rate, Kf or Kr, we can figure out the other one, or if we can measure both of these, we can figure out that, which we might not be able to measure otherwise, and then use that in the Gibbs free energy to extract more information. Okay, related to that is something that comes up even more commonly in biochemistry, which is the dissociation constant. So let's imagine a situation we have two molecules, A plus B, that complex each other. Let's say the simplest thing would be DNA. The A is a DNA molecule. We can label it easily, and B is some ligand, a protein, or which one would be the ligand? Depends. Think about it differently. So it could be a DNA binding protein, transcription factor, whatever. Or these could be two proteins, or a protein and a small molecule, or two small molecules, or receptor and ligand, any number of things. Experimentally, we're going to want to pay attention to that because the meaning is very different. If it's a receptor and a ligand, well, the ligand concentrations may vary widely while the receptor is stuck in a membrane, and we know how many there are, and indeed if it's on a membrane surface, and then the idea of concentration becomes a little bit funny to calculate, and that's why this becomes useful. So let's reverse this just to make it so it's clear that we're not talking about association constants. So let's imagine a complex disintegrating, dissociating to A plus B. Then the dissociation constant will be the concentration, product of concentration of A and B divided by the concentration of the complex. Okay, what's convenient here is that this, before I forgot to say this, that the rate constants here, the KEQ, right, is unitless. It's a ratio. Here, the dissociation constant has units of molarity, of concentration. So typically we think in micromolar and nanomolar and picomolar, millimolar, things like that. So units of concentration, which is much more convenient. This is why biochemistry for a dissociation constant to an association constant. An association constant has inverse concentration, and the numbers are very, very odd, while this is a very convenient concentration from which we can see meaning in a different way here. So let's think about this. At equilibrium, we're going to have the change in concentration of the complex doesn't change, so the change is 0, and therefore forward rate constant times the product of the reactants is going to be equal to the reverse rate constant times the concentration of the product. That's straightforward. Therefore, we can say that product of concentrations of A and B divided by that of the product is going to be equal to KR over KF, which is equal to the KD, and that's just convenient. Okay, how do we use this to measure? What can we do with this? Well, suppose that A is the DNA, and B is equal to a DNA binding protein. Did I spell protein wrong here? The idea would be we'd label the DNA, and we always have protein in excess. This is important. So what are we doing here? We're going to measure this by a gel. So we might have free DNA and bound DNA. The bound DNA is going to run slower on the gel, it's a native gel. So we have free DNA, and we can then add increasing amounts of protein. So how do we do this? We say this is the protein concentration. It's actually going to go up much steeper than that. And so without any protein, we only have free DNA. At very dilute protein, we have only free DNA. The protein doesn't show, only the DNA shows. The DNA is labeled, the protein is not. The protein is in excess, but we don't see it. And as we increase, then we get some DNA that's bound, and it shifts, it's delayed, it's retarded. And we will see through time that we have then this. And what's convenient then is that if we pay attention to this ratio of the free DNA to the bound DNA, we can monitor it there easily, and we can very easily see without any curve fitting, we can do curve fitting, but we can see a case where they're equal. So remember then, if we go back to this equation and we say the dissociation constant is equal to the product of A, concentrations of A and B, by that, at the case where concentration of A is equal to the concentration of the product, that's this point here, where the bands are equal, then these two terms are equal to each other, and Kd is equal to the concentration of B. So that means a concentration of B here. So that's really, really convenient for us. We can say that when we set it up this way, where the protein is in excess, in fact, we have to say, let's say that the total amount of protein is always much greater than the amount of A total. We can do it like that. Then this is true. And this is very convenient because we can say, this is the dissociation constant is the concentration necessary to bind half, or the concentration at which half bound. So we say dissociate constant is 10 nanomolar. That means at a 10 nanomolar, half is bound, half is free of the let's say, the membrane receptor. If we're thinking about membrane receptor and we have some ligand, it's like how much ligand is going to bind the receptor? The Kd is this, that means that this concentration happened. And it's a concentration, so it's very easy to think.